Hi everyone, now we are at eigenvalues and eigenvectors, lecture number 13. So this is continuation to lecture number 12. Four problems we did in lecture number 12, continuation problem number 5. Find the nature of the quadratic forms associated with this 3 by 3 matrices. So I want the nature of the quadratic forms, right? So first one in this, first 3 by 3 matrix is given. So for that x transpose A into x, right? This is x transpose. So x is column vector. So now this becomes row vector x, y, z. Let me write x, y, z. Or you can write x1, x2, x3, your wish. Okay. Next, A matrix. So 1, 0, 0, 0, 0, 0, and 0, 0, 2. Okay. And column vector x, that is x, y, z. X, y, and z. Okay. Now multiply this now x. So this is 3 by 1 matrix, 1 by 3 matrix, 1 row and 3 columns, 3 by 3. So resultant matrix is 1 by 3. So 1 row and 3 columns. So x into 1 x, y into 0 0, z into 0 0. So first entry is x. Okay. Second entry same with second column 0. Okay. Same with third column is 2z. Okay. So first multiplication of first two matrices gives this one. Next one is x, y, and z. Okay. Now multiply these two. What it gives? So this is equals to x into x, x square plus 0 into y is 0 plus 2z square, 2z square. So therefore the quadratic form Q is x square plus twicely z raised to. So this one directly you can write x square plus twicely z raised to, because look at only diagonal entries are present. Remaining all other entries are zeros in this matrix. So this is A11. A11 is nothing but x1 into x1, x1 square, or simply x into x, x square coefficient 1. Look at x square coefficient is 1. Similarly, y square coefficient is 0 and z square coefficient is 2. Z square coefficient is 2. So instead of writing like this, see if I write like this, for example, if this is so quadratic form, right? So after immediately seeing this one, generally what do you think? It is in only two variables x and z. Therefore, this is a quadratic form associated with a 2 by 2 matrix. But it is wrong. So the way of writing of this one is should be like this. So you should write like this. Instead of writing like this, you write q of x, y, z. You have to represent like this. Then only it will be very clear. Now it is x square plus y 2z square. So indirectly here y term is not there. So 0 into y, 0 into y square. Look at 0 into y square. Middle term is 0 here in this matrix. So therefore 0 into y square. So now it is 3 variable function, 3 variable quadratic form. Therefore it is also associated with 3 by 3 matrix. Fine. Now we have to classify what kind of quadratic form it is and what is the nature of this quadratic form. Okay. Now, so this one, since x square, whatever x you choose here, since it is x square, it is always positive. Z square, whatever z you choose, it is always positive if they are non-zeros. Okay. Therefore, I can say that this is strictly more than 0. Okay. For all strictly more than 0, for all x not equal to 0. Here x means what? Let me write clearly. So this is, instead of writing like this, so this is more than 0 I can write. Can you choose any other numbers such that this is equal to 0? So if I choose, see this one I can write as, or you can write this one as, let me write first, after that I will give the sign for that. Or you can write like this, or this quadratic form you can write like this also, q of x comma y comma z is equals to x square, right, plus twicely z square plus 0 into y square, because look at the matrix, the diagonal entries you look at 1 0 2, so 0, this is y square coefficient, that's why 0 into y square. 0 into y square is 0 only, no need to write, just we are giving the sign to this quadratic form, that's what I am writing 0 into y square. Now let us investigate the sign of this quadratic form. So clearly, so therefore q of x y z is equals to x square, right, plus twicely z raised to plus 0 into y square is more than 0, because all these are positives, right? X is, if x is negative, x square become positive. If z is negative, z square become positive. So sum of two positive numbers is positive, that's what more than 0 I am writing. When it is equal to 0, if it is equal to 0, then I can write it is more than or equal to 0. Once it is more than or equal to 0, then according to definition it is positive semi-definite. If it is only more than 0, it is positive definite. Okay, we need to search that also. Can you find such kind of vector or not? Look at here. Let I am choosing this column vector. Let x is equal to 0, uh, 0 and 1. I am choosing this column vector. Is it equal to 0? It is non-zero because last entry is present. So it is non-zero vector. Right. Now at this vector, what is this quadratic form value? So therefore q of x, y, z value is equals to x value, small x is 0, small y is 0 and small z is 1. Okay. Now let us substitute that. So 0 square, I am substituting here 0 square plus 2 into z square. What is z value here? 1. Z value 1, right? So let me write instead of this, yeah, let us choose the different one. So yeah, 0 1 0 I am choosing 0 1 0. Again it is not equal to 0, right? Yeah, 2 z value is what? 0. So 2 into 0 square plus 0 into what is y value? Y value is 1. So 1 square. What is this value? Equal to 0 only. Now quadratic form equal to 0 for non-zero x. So therefore final conclusion is therefore q of x comma y comma z is, which is nothing but x square plus twicely z raised to is more than or equal to 0. For this vector it is equal to 0, right, and remaining all vectors it is more than 0. Therefore final comment is therefore q is positive semi-definite, positive semi-definite. Okay, so this is a classification of the first matrix quadratic form. Similarly, second one, number 2, let's call the matrix is A. So the matrix is minus 2 minus 1, so minus 2 0 0 and 0 minus 1 0 0 0 0. So this, for this matrix the quadratic form directly I am writing. So therefore since it is 3 by 3 matrix, so we need to write as a 3 variable function 3x1 x2 x3 or xyz, your wish. The only thing is you have to choose 3 variables. So this one is a11, right? A11 is minus 2. A11 is nothing but x1 into x1 square. So x1 square coefficient is minus 2. So minus 2 x1 square. Directly you can write. Or just now I did x transpose a into x, like that also you can find your wish. Next, all remaining all other entries are 0. Just concentrate on diagonal entries. And this entry is a22. A22 means x2 into x2. Second variable into again second variable because it is a22, right? Already I told you a22. This 2 Just remember like that. This 2 shows second variable, again 2, again second variable. So you remember like this. So x2, second variable is x2 into again x2. That means this is x2 square coefficient a22. Like that you remember. Okay. So its coefficient is minus 1. So minus x2 square. Okay. And 0 into x3 square. So that is not required. So finally this is the quadratic form. Now we need to investigate its sign. Okay. What kind of quadratic form it is. So you take minus common here. So after taking minus common, 2x1 square plus x2 square. See x1 square, x2 square, sum of two squares is always positive only, but in front a negative is there, therefore it is less than 0. It is always negative, you choose whatever the numbers. We need to investigate whether for what value it is equal to 0. Okay, so for that, so this quadratic form you write like this: q of x1, x2, x3. This is nothing but minus 2 times x1 square, okay, minus x2 square, and x3 variable is option. So plus 0 into x3 square, because look at a33 value is 0, 0 into x3 square. Okay, now so let choose one vector at which this expression is, this quadratic form is 0. Can you choose such thing? So x1 0. So let me write first the vector, column vector x1 x2 x3, and I am choosing the values like this. So which is, now I am choosing x1 is 0, x2 also 0 I am choosing, x3 is some 1 I am choosing, or 2 3 whatever. So simply this is not equal to 0. Okay, non-zero vector you have to choose compulsory. At this, what is quadratic form value? So therefore q of x1, x2, x3, okay, which is equal to minus 2 into x1 value 0, 0 square. Okay, next minus x2 value 0, so 0 square. Okay, next plus 0 into x3 value 1, 1 square. So finally this is 0. We are getting 0. Look at, it's a non-zero vector with the quadratic form becoming vanish. So finally, so overall comment is, so therefore the given quadratic form q of x1, x2 and x3, this one, which is nothing but minus 2x1 square, okay, minus x2 square is less than or equal to 0. So therefore the quadratic form is, the quadratic form is negative semi-definite, negative semi-definite. Okay, this is negative semi-definite. Okay, similarly third one, what is third one? Minus 1, minus 3, minus 2, call the matrix is A. So minus 1, 0, 0, 0, minus 3, 0, and 0, 0, minus 2. Check once again. 3 minus 2, yeah. So same, so directly I'm writing what is quadratic expression. So directly q of, let me write x, y, z, q of x, y, z, so minus x square, okay, minus 3y square, minus 2 z square, right? So if you take one minus common, minus of x square plus 3y square plus 2 z square. So this is always less than 0 only because of minus. Now can you choose a vector x such that this quadratic form is equal to 0? So can you choose such thing? So you can choose like this. For example, if you choose x is this one, but I want only non-zero vector, right? if you choose xyz is like 0 0 0, then only this quadratic form is 0. For any other vector, this is less than 0 only. But I don't want this kind of vectors. What I want? I want non-zero vectors I want, right? Non-zero vectors I want. Okay. So therefore, this kind of vectors we should not choose. So therefore, it is not equal to 0, only less than 0. Therefore, finally the comment is, what is this? Therefore, Q is negative definite. Negative definite because it is less than 0. So like this we can classify the given quadratic forms. Okay. Next one theorem. So this theorem again, this theorem about the classification of quadratic forms. So far what we did just to give the sign of the quadratic form, that means x transpose ax is positive or negative or more than or equal to 0 or less than or equal to 0. Depending on that we classified the quadratic forms so far. Now this is depending on eigenvalues. Okay, now look at this. Given a quadratic form Q, okay, x transpose A into x, and let lambda 1 to lambda n are real eigenvalues. Concentrate on this, real eigenvalues. Okay, so here A is n by n matrix, therefore n eigenvalues exist. Whatever they may be, but n eigenvalues exist. They may be repeat, sometimes they may be negative, they may be positive, sometimes some eigenvalues are zeros, whatever, but n eigenvalues exist because A is n by n matrix. Okay. Then, so depending on these eigenvalues, now we can classify the nature of the quadratic form. Look at the first conclusion. The quadratic form is positive definite if and only if all the eigenvalues are strictly more than 0. That means positive. Okay. Similarly, second conclusion. The quadratic form is negative definite if and only if all the eigenvalues are less than 0. All the eigenvalues are negative. So examples, for example, look at here. What are the examples for this? If eigenvalues are 1, 5, 7, for example, 3 by 3 matrix we have. For the 3 by 3 matrix, eigenvalues are 1, 5, 7. Then that is called positive definite matrix. For example, A is a part of 3 by 3. Okay. A is a part of 3 by 3. Right? 3 by 3 matrix, 1, 5, 7 are the eigenvalues. So therefore, the matrix A is a positive definite. The quadratic form corresponding to the matrix A is positive definite. And here what kind of values? Negative. So that means -1, -2, some -4. This kind of values exist. These are eigenvalues like that. Okay. Similarly, next conclusion. The quadratic form is positive definite, positive semi-definite if and only if eigenvalues are more than or equal to 0. What is the difference between first and third statement? Here is strictly more than 0. Here is more than or equal to 0. At least one eigenvalue is 0. That means the eigenvalues may be like this. It's 2, 0, 5 like this. So at least one eigenvalue must be 0. Sometimes two eigenvalues exist. Okay, like that. All the eigenvalues are more than or equal to 0. Then such a matrix and such a quadratic form is said to be positive semi-definite. Next conclusion. Q is negative semi-definite if all the eigenvalues are less than or equal to 0. Example, -1, -3, 0 or -2, 0, 0 like this. At least one eigenvalue should be 0. If these kind of eigenvalues are existing, then the corresponding quadratic form is negative semi-definite. Okay. Next conclusion. Indefinite. Q is indefinite if and only if all the eigenvalues are more than some eigenvalues are more than or equal to 0 and some eigenvalues are less than or equal to 0. So it is a mixing. It's like khichdi kind of. Okay. See, for example, eigenvalues are -1, 3, 0. Look at one negative eigenvalue, one positive eigenvalue, 1, 0. Or sometimes like this, -3, 4, 5, like this. Okay. Or you can look at 3, 1, -2, like this. So it is a mixing of both positive, negative, and sometimes 0. Then such corresponding quadratic form is said to be indefinite quadratic form. So this is a classification with respect to the eigenvalues. Okay. Here we go one problem. Find the nature of the quadratic form associated with these three matrices. Already this problem just now we did, but we did by using the concept of assigning the sign of the quadratic form x transpose x. If it is more than 0, positive definite. If it is less than 0, negative definite, like that. We are giving sign to the x transpose x here, right? Just now we did. Now through eigenvalue concept, let us classify the corresponding quadratic forms. Now look at here, first one, this one. So since it is diagonal matrix, what are the eigenvalues? Eigenvalues are diagonal entries. Therefore lambda 1 is 1, okay, and lambda 2 is 0, and lambda 3 is how much? 2. What kind of eigenvalues are existing? All are positive. One is 0. At least one eigenvalue is 0. Therefore, it is positive semi-definite. Third statement. So, therefore, conclusion is, so therefore, Q is positive semi-definite. Semi-definite. The corresponding quadratic form. First, we find out what is a quadratic form. Quadratic form is x square plus 2z square, right? X square plus 2z square. That is positive semi-definite. Just now we did already. Positive semi-definite. Let me go back. Same problem. Look at this problem. Look at positive semi-definite. We conclude here. Positive semi-definite. Same problem only. 1 0 0 0 0 0 0 0 2. Understood? Same problem. We are proceeding by the concept of eigenvalues. Okay. So now similarly here for the second problem. Again, since it is diagonal matrix, eigenvalues are -2 and lambda is -1 and lambda 3 is 0. Look at all the eigenvalues are negative and 1 is 0. Therefore Q is conclusion. Therefore Q is negative semi-definite. Negative semi-definite. Negative semi-definite, like that. Okay. Next, similarly this one. Again, it is diagonal matrix. So lambda 1 is -1 and lambda 2 is -3 and lambda 3 is -2. All the eigenvalues are negative. So therefore Q is negative definite. Q is negative definite. You write the statement, then conclude Q is negative semi-definite. That means this statement you have to write. Q is negative definite if and only if. It is if and only if statement. Okay? It is not one. If Q is negative definite, we can say that lambdas are negative. Not like that. Lambdas are negative. Q is negative definite. If Q is negative definite, I can say that lambdas are negatives. Like that. Okay? It is if and only if statement. Both directions, the statement is true. So this is about through eigenvalues concept. Similarly, let us do one more problem. Problem number, this already I did in lecture number 12, problem number 4, same problem. But I want to find the nature by using eigenvalue concept. Okay, now let me do this. So first one, so matrix A is given, that is 1 1 1 5. Now through eigenvalue concept, I require first what are the eigenvalues, right? So first let me compute the eigenvalues. A minus lambda L, that means characteristic equation you need to calculate. That means, so 1 minus lambda, 1, 1, 5 minus lambda. Okay, and this will be equal to 0. And this implies, what is characteristic equation now? So 1 minus lambda into 5 minus lambda, 5 minus lambda, minus 1 equal to 0. Then 1 5 is a 5, minus 1 5 is a 5, and minus lambda, minus 5 lambda, minus 6 lambda, and plus lambda square. Okay, and minus 1 equal to 0. So finally lambda square minus 6 lambda plus 4 equal to 0. Now minus b plus or minus b square minus 4 is by 2 a form. So minus b plus or minus b square 36 minus 4ac. 4ac 16, right? 16 by 2. Okay, so these are lambdas, right? Lambdas. What will you get? So 6 plus or minus 36 minus 16, 20, 20. So 2 root 5 I can write 20, root 20, right? 2 root 5 by 2. So that means These are, so 3 plus or minus root 5. Okay, that means eigenvalues are lambda 1 is equal to 3 plus root 5. Okay, and lambda 2 is 3 minus root 5. Now what kind of eigenvalue these are? So 3 plus root 5 is always more than 0. What is root 5 value? 2 point something, right? 2 point something. Here also 2 point something, but 3 minus 2 point something is more than 0. So both are positives. So therefore it is positive definite. Positive definite. Which one positive definite? Q is positive definite. Q is positive definite like this. Okay. So similarly for the second one, yeah. Like this, first you need to compute what are the eigenvalues. After that, you can comment or classify the given quadratic form 1 3 3 1. Now, again, same story. So, a minus lambda I, which is equals to 1 minus lambda 3 3 1 minus lambda. This is equal to 0. Now, this is 1 minus lambda whole square minus 9 equal to 0. Okay, and simplify this lambda square minus 2 lambda plus 1 minus 9 equal to 0. Okay, now lambda square minus 2 lambda minus 8 equal to 0. Now factorize 4 to the 8. So I can factorize like this: lambda square minus 4 lambda plus 2 lambda you can write. So that if you simplify, minus 2 lambda will get minus 4 to the minus 8. Minus 8 equal to 0. Or we are having this formula, you can apply in this formula. So now lambda is common, lambda minus 4, right? And 2 common, lambda minus 4 equal to 0. So overall lambda minus 4 common, lambda minus 4 into lambda plus 2. So therefore eigenvalues are, so therefore what are the eigenvalues? Therefore lambda 1 is 4, 1 eigenvalue, and lambda 2 is minus 2. Look at, one is positive, one is negative. So therefore this is what kind of quadratic form? So therefore Q is indefinite, right? Indefinite, last statement in the theorem. Indefinite. So like this we can classify the quadratic forms associated with the respected matrices. Okay. Next one definition. After this I will proceed one more way of classifying quadratic forms. Okay. So now in this, leading principal minus. For example, so roughly I will explain what is meant by leading principal minus, because these two terminology I will use in the theorem, next theorem. Leading principal minus and principal minus. Okay, so let A is, assume the matrix is just this. Let matrix A is A11, A12, A13, and up to so on A1n. Okay, next second row A21, A22, A23, and up to so on A2n. Okay, and next one A31, okay, A32, A33, and up to so on A3n. And last row is, I am taking an n by n matrix. Okay, taking an n by n matrix. Yeah, and last one an1, an2, an3, and up to so on ann. So here dot 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 up to so on. So it is also up to so on. It is also up to so on. Okay. So I have taken n by n matrix. The order of this matrix is n by n, right? Now leading principal minus means, so concentrate on this only first entry. So this one. So let us call this one is some D1. D1. Determinant of D1 is nothing but A11. Okay. Next to D2. D2 means this one. This 2 by 2. Because here leading element is A11. So with respect to this leading element, we are finding all the minus, principal minus. That's what leading principal minus heading. Now I generated 2 by 2 matrix, right? So that is what here A11. So this determinant is called D2. Okay. A11, A12, and A21. Okay, A22. Okay, this one. Similarly, next one, this one. 2 by 2 is over. Next to 3 by 3, how to take this one? That means, so here D3 is next one, determinant of, not modulus of, determinant of. There is a lot of difference between modulus and determinant, because look at first one. If you call it is modulus, for example, this entry is minus 2, modulus of minus 2 become plus 2, but it is not modulus, it is determinant. So therefore, if A11 is minus 2 here, then what is determinant of D1? Minus 2 only. Don't remove minus because it is not modulus. We need to find the determinant. Okay. Similarly here also, A11 into A22 minus A21 into A12. That I will write, but I will not multiply the minus or plus like that. We are finding only determinant. Fine. So now determinant of this one is A11, A12, A13, and A21, A22, A23, and A31, okay, A32, A33. So this is D3, and up to so on. The last one is Dn. The last one Dn is nothing but whole matrix you have to take. At the end I will get entire matrix, right? That means this minor I will take. This minor is nothing but entire matrix A. Okay. So this is about leading principal minus. So these are said to be are leading principal minus. Okay, this is leading principal minus. Next one, principal minus. Same matrix you take quadratic forms. Theorem number 2. Given a quadratic form Q where A is an n by n matrix, square matrix, then look at the first conclusion. The quadratic form Q is positive definite if and only if the leading principal minus are positive. The leading principal minus are positive. Leading principal minus means already just now I told you D1, D2, up to so on. All these should be more than 0. Then I can say that the corresponding Q is said to be positive definite. Okay. Similarly, second statement. This quadratic form Q is negative definite if and only if the leading principal minus. Look at the word leading principal minus, not principal minus, leading principal minus. Here also leading principal minus. Okay. Leading principal minus are alternate in sign change starting with the negative 1. That means first D1 should be less than 0, D2, determinant of D2 should be more than 0, and D3 less than 0, D4 more than 0, like that. Starting with compulsory negative. Compulsory should start with negative. Okay. Then next one should be positive, next one should be negative, like that. Then I can say that if this pattern is following, then the corresponding quadratic form is said to be negative definite. Next one. The quadratic form Q is indefinite if and only if some non-zero decay violates the above sign pattern. For example, look at, I am getting, let me explain here. For example, I am getting D1 is some 2, okay, and determinant of D2 is some 5, okay, and determinant of D3 is equal to some minus 1, and determinant of D4 is equal to some 7. Let us take 4 by 4 matrix. Okay, all these are okay, positive only, but this one is violating the condition. See, this is non-zero only, right? That's what I'm telling here. some non-zero decay. So this one now D3. Here K means here 3, particularly for this example K is 3 here. So this one violating the condition. Which condition? This entire first condition is violating. Then such a matrix and such a corresponding Q is indefinite. Look at once again, the quadratic form Q is indefinite if and only if some non-zero decay violates the above sign pattern. Above sign pattern, either this or this. For example, this sign pattern is following perfectly. For example, look at the second example. Yeah, look at this. So you're getting d1 is some minus 1, okay, and d2 is some plus 5, and d3 is some minus 2 you're getting determinant, and d4 you're getting some minus 5. Look at this is okay, this is okay, this is okay. Starting with negative, negative, positive, negative. Next one should be positive, but I got minus 5. So now d4 is disturbing. So this non-zero decay is disturbing, it is violating the condition. Therefore, such a quadratic form Q is said to be indefinite. Okay, hope you understood this. Next one, I have to erase this, I think. Yeah, next one. Let me erase this. Okay. Now look at the next statement. I have given a different color. That means so far we concluded by using leading principal minus. Okay. Now we have to conclude by using principal minus, just principal minus. Look at here. All the principal minus and so MK I am denoting. So if all are more than or equal to 0, that means at least one determinant should be 0. Okay. Then such a quadratic form should be positive semi-definite. Okay. Similarly, second conclusion, the quadratic form Q is negative semi-definite if and only if all the principal minus, again principal minus, all the principal minus, m2k plus 1 is less than or equal to 0 and m2k is more than or equal to 0. It means what? For example, k is equal to 0, what will get m1? So I want m1 should be less than or equal to 0. If k is equal to 1, m3. That means odd determinants are negatives. Next, k is equal to 2, what will get m5? So this all these odd determinants are negatives and even determinants are positive. If k is equal to 1, you will get m2. All 2 by 2 principal minus, these are. Okay. Next, k is 2. K is 2, you will get 4. All 4 by 4 principal minus should be more than or equal to 0. If k is 3, m6, like this. So all even determinants are more than or equal to 0 and all odd determinants should be less than or equal to 0. Then I can say that the given quadratic form is negative semi-definite. Okay, negative semi-definite. So indefinite means some decay violates the above sign pattern. So this is about again classification by using principal minus and principal leading principal minus and principal minus. Now let's have one problem depending on this theorem number 2. Problem number 8. Find the nature of the quadratic forms associated with these three matrices. Now look at the first one. Now we have to classify the corresponding quadratic forms. So now with respect to this matrix, let us assume the matrix is A, the given matrix is A, and 4, 2, 0, 2, 9, 0, and 0, 0, 2. So 3 by 3 matrix of order 3 by 3. Okay. So yeah, so principal minus, leading principal minus or principal minus, whatever. First let me find out principal minus first. Okay, principal minus. So for that, d1, what is d1 now? d1, determinant of 4 is nothing but 4 only. Again I am telling, if it is minus 4, d1, determinant of d1 is nothing but determinant of minus 4 is equal to minus 4 only. Okay, don't remove minus, it is not modulus. Okay, fine. Next, I want d2. Now what is d2? This one, right? So determinant of 4, 2, 2, 9. What is this? 4 9 is 36 minus 4 is 32. Okay. Next, what is D3? The given matrix, right? Determinant of D3 is nothing but determinant of A. Okay. Now, what is determinant of A? So 4 into 9 to the 18 minus 0. Okay. And minus 2 into 2 zeros are 0, 9 zeros are 0. And 0 into that is 0. Okay. So this will be 72. So therefore I got all are positive. So therefore conclusion. So determinant of D1 is more than 0. Determinant of D2 is more than 0. And determinant of D3 is nothing but determinant of A, which is also more than 0. So therefore conclusion is, what is the conclusion? By first statement, look at the theorem. Look at all the determinants are more than 0. So therefore Q is positive definite. Therefore Q is positive definite. So conclusion is, so therefore Q is positive definite. So like this also can conclude. Or you can find x transpose A into x, you will get a quadratic form, give the sign change to that. Or you can find the eigenvalues to this matrix, and depending upon eigenvalues also I can conclude. That is one way, and this is by using determinant concept. Okay. Similarly for the second one, so this is the first one, third problem. Minus 1, 0, 0, 0, minus 3, 0, and 0, 0, minus 2. This problem I already did, but I want to classify by using the concept of determinant. Okay. Now let us find the leading principal minus. If it is not working, then I will go to the principal minus. So now first D1. What is determinant of D1? Determinant of minus 1, which is minus 1 only. Okay. Next, what is D2? T2. So that means minus 1, 0, 0, minus 3. Now what is the det of this? 3. So this is less than 0, this is more than 0. Next, determinant of D3, 3 by 3 matrix, which is nothing but the given matrix. What is the given matrix? Det minus 6. Because it is a diagonal matrix, eigenvalues are minus 1, minus 3, minus 2. Det is nothing but product of the eigenvalues minus 6, which is less than 0. Look at sign pattern is following. Starting with a negative, next positive, next negative. Therefore, conclusion is, therefore, Q is negative definite. Okay. If all are positive, Q is positive definite. Then it is Q is negative definite. So with this, I will stop. In the next class, we will discuss one more way of classifying the quadratic forms. Okay. With this, I will stop.